All right, here we are. It is 7 p.m. I am this is Mr. Jern here, going to go over Unit 8. This is the electromagnetism unit. We have our test coming up in a couple days. And this one is surprisingly challenging in a different way than some of the other units we've done. This one involves no math. So it's all memorization. It's all like hand stuff and all that. So just kind of be prepared. It's a different kind of unit to prepare for. So I just want to let's see. Here's the thing: electromagnetism, right? It involves electricity. It involves magnets. And at the beginning, we talked about magnets. The previous unit was all about electricity. And then I think where we kind of ended up here at the end is the combination of the two, like how they come into play. So before I get too much further, just a couple things. There is the chat. You can feel free to respond there, ask me questions, knowing that I will, there's like a 10-second delay. Excuse me. If you have a question, you can send it to the Parent Square app, and I will be able to reply to any questions you might have. So where was I? So one other thing is be ready to take some notes. Like watching this in the background is great. It's mildly helpful. It's better than nothing, of course. And I don't know how well the captions do with my voice if you're watching this muted. The auto captions is, tricky, but take notes, write stuff down. All right, use the Cornell notes that you have. Okay, well, let's begin. So there's I broke this unit up into two parts. The first one was just the magnetic field, the basics about how a magnet works, beyond what you learned when you were younger. So a couple questions to talk about here. What happens when you break a bar magnet in half? We've seen some diagrams. You may have actually accidentally broken a magnet in half, whether in class or not. I don't know. But what happens is, here's our choices. They each become magnets with a north pole and a south pole. Each become magnets, but one is a north pole and the other is a south pole. Now that one, we could just start eliminating some things. This is just not true. The North Pole and the South Pole, you cannot separate them. So that's just not going to be an option. So just keep that in mind. The domains, scatter. Ooh, okay. So what we have here is a keyword, domains, and that might draw your attention. Excuse me. Don't be distracted when you see a keyword like this, especially on a test in a unit where there's no math and it really is just all memorization. Okay, so these are the tricky parts, the things that are there that might throw you off. All right, so just because it has domains, the word domains in it, doesn't mean it's the correct answer. And that's not what's going to happen. So the domains are not going to just scatter just because it's been broken in two. So that's not wrong. That is not correct. They become charged. Ooh, another thing. We've been talking about charged objects. Well, okay, once again, it's a misdirection. Just because it's mentioning something that we talked about does not mean it's the correct answer. So, of course, if you have been paying attention, you know that the correct answer is A. They each become a magnet with a north pole and a south pole. And the reason it does have to do with domains is because every single little magnet that you might have is made up of little tiny clusters of clusters of atoms that are all magnetic. So like every single atom of iron is magnetic, and you might get a group of them together, and they're going to point from north to south, and then another group over here is going to point from north to south, and then a bunch other here are going to point from north to south, north to south, north to south. And in a magnet, that's what it's going to look like. They're all pointing from the north to the south pole. And if you break that in half, well, okay, they're still pointing to the south, and they're starting from the north. So that's why you could break a magnet in half and still have two magnets. Let me know if you need any clarifications. Okay, the source of all magnetic fields. This one was missed a lot on the quiz. The quiz, I think, threw a lot of us off. No, the quiz exposed a lot of things that you might have needed to review. So make sure you go through that quiz because you'll see a question very similar to this one. Negative charges. So this is the source of all magnetic fields. And I believe there was a choice on the quiz that involved the word domain again. That is not the source of magnetic fields. That is just a group of, here, it's not on here, so I'm kind of making it up. I'm going to like letter E, domains. Okay, you might, I don't think I have an option with that here. No, I don't. But you might see the word domains again. That is not the source. That is just a name for a clump or a cluster or a group of atoms that are all facing the same direction. Okay, that is not the source of them. The domains, going back here, the domains lining up is important for a full-on magnet, but domains are basically like little tiny itty-bitty mini magnets. Okay, so they are not the source of the magnetic field. They themselves have a magnetic field, but they're not the source. So this letter A is often chosen, but it is absolutely not correct because it doesn't have to do with negative charges lining up or being forced to one side. That, by the way, was something we've talked about. That might be something like a battery, where you have a positive end and a negative end, a negative and a positive terminal, and all the negatives are forced to one side, and that doesn't mean it's a magnet now. That just means it's become polarized, maybe, where it's, yeah, so anyway, that's the wrong answer. It has nothing to do with the negatives all being on one end or the other. Gaining electrons, that sounds suspiciously like becoming negatively charged, so that can't be it. Charged particles that cease moving, okay, that's the correct answer is D, charged particles that are moving. That is the source of magnetic fields. All right. So like I said, send me messages, type it in the chat if you want to. Okay. All right. What makes a piece of iron magnetic? Hey, I already talked about this one. The domains are mostly lined up in the same direction. Well, that's going to be the correct answer. I've already talked about that. That's it. I drew my wonderful magnet here. Look, I cannot get that top corner right. And the domains are all facing more or less in the same direction. That makes that a magnet. Once again, the more positive charges on one end and more negatives on the other, that no, right? So don't get those confused. Make sure you got that. Unpaired electrons in each atom stops moving. Okay, stops moving. It has to be moving. Going back to our previous question, charged particles that are moving. Okay, they have to be charged and they have to be moving. If either one of those conditions is not true, you don't have a magnet anymore. Okay, so definitely not. It starts to spin around. What starts to spin around? The iron? No, it's just kind of like picture that. Come on. Okay, the domains are mostly lined up in the same direction is the correct answer. All right. A magnetic domain. This might have been a question I could have asked first, but I didn't, because now that I've kind of invoked it many times, I've brought it up a few times. Let's once and for all define what a domain is, a magnetic domain. If you remember the video I showed you, Veritasium, the guy with the swords and all the sword guys all lined up in a clump in that area, and they are all pointing in the same direction, but the nearby groups were pointing in a different direction. That's what a domain is. So what is the written definition of a domain? It's a group of magnetically aligned atoms. That's it. All right. So all the rest of those are, letter B is wrong. It's not the source. It's not a cluster of charged particles. No. It's magnetically aligned atoms. Okay. So here's another diagram. I found it on the internet. You just Google magnetic domains, and this is one of those ones that pops up. So I did not make this, but this is an example of what a domain might look like. And the domains are represented by these blue and red stereotypical magnets. So in the case on the left, they're all scattered and random, and so this this piece of material right here would not be magnetic. But over here, all the domains are all nice and lined up. That would be magnetic because all the red norths are pointing in the same direction. All the blue souths are pointing in their same direction. Okay, so all the red is one way, all the blue is the other way. That's what a domain is. Here, write it down if you haven't, and memorize it. There's a lot of definitions out there, but that's basically what it is. It's a group of magnetically aligned atoms. They're all magnetic and they're aligned. They're lined up. All right. So far, so good, right? I mean, this is magnetism. Not too bad so far. I know most of you are here because of the left-hand rule and the right-hand rule, but we're getting there. All right, why does heating a magnet or banging it on something hard weaken it? You might not remember, but when we did our lab with the iron magnet and you had to sprinkle the iron filings all over it, I might have asked you to be careful and not drop it because what happens is, looking at the domains again, if you start off with your magnet looking like this, okay, that's your initial, to use the words we've been using, that's not an initial. If that's your initial, let's see if I could just do this. Ooh, fancy Mr. Jern with his keyboard shortcuts. Your initial magnet. So this is the one I gave you, magnet. And you drop it, what happens? Well, all these meticulously aligned domains get knocked out of a, they get knocked around, they get jostled up, all right? It's like, I mean, picture this. Here's an analogy. We spend 10 minutes in class and we perfectly line up all the desks to be perfectly spaced, perfectly placed, perfectly facing the correct direction, right? And then an earthquake hits. What's going to happen to our perfect structure? Well, bad things. It's going to get messed up. And so that means the answer is B. The domains get knocked out of alignment. Okay, that kind of addresses, where'd my little mouse thingy go? Come here. There you are. Okay, I couldn't find it. Where'd it go? Something hard. Banging on something hard will do that. But what about heating it? Yeah? Heating it up. Here's what it does. And I'll mention this in class too. Heating it up, heating anything up adds energy. Okay, imagine water. It's cold, it's just sitting there nice and still. And you put the water on you put a pot of water on the stove, you let it heat up. What starts to happen? It starts to gain energy. It starts to get like all churny and boily and moving around a lot, right? It gains a lot of kinetic energy, you might say. That's the same thing that happens with anything. You add energy and you can't see it. It's not as like boily bubbly as water, but the atoms that everything is made up of starts to jiggle around a lot more and they start to bounce around each other and you add more heat. And that's what heat is. Heat is just the molecule, essentially. The molecule is moving around faster and faster and banging into each other. That's why heat is bad. Too much heat is bad for you. If you burn your finger, what did you just do? You literally added so much energy that your molecules of your finger just kind of like, right? And so anyway, that's what happens with a magnet. So never heat a magnet, okay? You could freeze it all you want. Freezing is the opposite of that. You're literally taking away energy. And so theoretically, a magnet might last longer. Anyway, so that's the answer. Domains get, so letter A is definitely not true. Letter C, that's the little, you still get, we already discussed that, question number 1. And letter D, I mean, as sensitive as magnets are, they actually don't get hurt. Their feelings don't get hurt by this. They'll be okay. Okay, long answer to a short question. What seems like it might be the cause of the Earth's magnetic field? All right, this is, I drew a wonderful picture on the board. I'm getting an error message. I'm going to just check something really quick. Okay, I think we're good. Sorry about that. So I drew this picture on the, okay, you might be experiencing buffering. I apologize if that is happening. I don't know why. I'm just gonna keep going. So if it's getting too bad, just send me a message or something like that. I will see if I could address it, but I might just, sometimes YouTube is a little funny like that. It gives me messages and it's like nothing's really wrong. Where was I? Oh, so I drew the part in my quick drawing here. So here's the Earth. Here's the core of iron and nickel, and it's pretty solid, all right? And I'm gonna be wildly out of scale here. I am a physics teacher right now, not a geology teacher. So in the middle here, let's switch colors. Where'd my thing go? Whoop. Oh, way over here. All right, let's do this. It's important that I do the right color here. Come here. Hey, we did this last time. Okay. I will not be switching colors. Oh, will I be able to switch back? That will be the question. So this part right here is the swirling mess of magma, and inside the swirling mass of magma in the center of the Earth are, or at least the inner I cannot think of the word. It's beneath the crust of the Earth. Anyway, the answer is definitely not magnets on the ground. Magnets on the ground is silly. I mean, if you think about it, magnets on the ground. Okay, first of all, if there were that many magnets on the ground, people would have picked them up a long time ago. Secondly, if there were magnets on the ground, they would be all randomly scattered. They would not affect anything. So no. Letter B, the core is a giant magnet. Okay. That's fairly plausible, I suppose, but scientists have ruled it out. So the core is not a giant magnet. No. Flowing magma under the Earth. Yes, look for the word magma, flowing, moving magma. That's going to be your answer. The Earth's rotation is not it either. It's going to be that magma. Okay, so very good. There we go. All right. What three materials can become magnetized? I hope you guys know this by now. Copper, iron. What the is wrong with me? Holy cow, guys, do not choose copper. I fell into, like it's right there. It's like copper. I wanted to choose copper. You will want to choose copper. Don't choose copper. Okay, iron, nickel, and cobalt. Okay, go like in the order that you memorized it. I memorized it in that order, so go in that order. And that, like, I saw copper and I saw the C and I'm like, oh, C, copper, coal. It even starts with an O, and then it's like, it wasn't it. So go in the order you memorized it and look for them and eliminate them. So I remembered it, iron, nickel, and cobalt. So that was the order I circled them in. Let's memorize it. It has to do, you don't have to remember why, but okay. This question was missed on the quiz a lot, and I understand why. Rank on the quiz, I think I asked, where is the magnetic field strength the strongest? And a lot of you chose B, and I get it. It is the closest to the magnet, right? It's like right there, come on. Okay, that is not how you figure out what is the strongest. You figure out what is the strongest by which is closest to the pole. Now they're all far from the South Pole, so I'm gonna ignore the South Pole. But look at this, starting in the North Pole, I got a line that goes like this to A. I got a line that goes like this to B. I got a line that goes like this to C. And I got a line that goes like this all the way to D. Okay, so keeping that in mind, what's going to be the strongest? Well, it will be A is the strongest, right? And then B, which is the one that a lot of you chose on the quiz. Again, understandable because it's close to the physical magnet, but it's got to be close to the pole. All right, and then C, and then D. Hey, look, it's in alphabetical order. Don't expect that on the test. It might be, but it probably won't be. So yeah, A is closest to the pole, and then B, and then C, and then D. Okay, closest to the pole. Which most correctly shows the shape of the magnetic field around a magnet? Okay. A looks like, I don't know what's going on here, because some of them are pointing in, some of them are pointing out. That is, no. C's got some craziness going on. Look at this. It's going from South Pole to South Pole and North Pole to North Pole. No. The trick is, remember, it always goes from North Pole to South Pole. And so B is our answer. Right? Oh, this is a little tricky. I don't know if there's going to be anything this tricky on the test, because you might be like, wait a minute, what about this? This looks like it's going from north. But then on the bottom is going from south to north, and that would be easy. I feel like, I don't think that question is going to be quite like that on the test. But just remember north to south, okay? North to south, and you'll be good. Still no questions. All right, you're just listening. I like that. Listening intently. There is snuck into our electromagnetism quiz test a Newton's third law question somewhere, somehow, okay? It's not bad. It sneaks into the test every now and then. That's fine. But I just want you to be aware that you got to remember all objects, how do I say this? For every action, there's an equal and opposite reaction. If something pulls on something, hi Romeo, how you doing? If something pulls on something, then the other one pulls with the exact same amount of force. All right? So they are the same. I get all excited writing things. So same. Okay? They are the same. It doesn't matter that one of them is bigger, the other one's smaller. I don't know if you remember in class, but I had two people stand up in front of the classroom and try to pull on the two scales and make them say different things. And I said, no, one person pull harder, one person pull less. It doesn't work. All right. Same thing is going on with the magnets and anything. Okay. If you have one hand standing still and you slap it with your other hand, your hands hit each other with the same amount of force. You feel tingly in both hands. Okay, equal and opposite. Just remember that. It's a big one. Something's going on. Oh, I touched something. Let's go. Here, we'll just make that into a smiley face. Okay. All right. It's not advancing. Let's try. Can I go to the next question, please? Oh, wait, what? Oh, that's why. What was I thinking? I made this like weird. Okay, I apologize about that. My PowerPoint is funny. So yeah, they are, is there a fourth option? No. They're the same. They pull with equal force. All right, I said it all. So just to make this complete, I will circle that. Okay. All right. I believe this might be, no, we're getting near the end of this first part though. Which shows two magnets with opposite poles together? Opposite poles, opposites attract, okay? So our answer, of course, is going to be B, because you can just see, let's see if I can do this. Whoop, yay, okay. So you can just see here with my laser pointer that we've got a north and a south pole right near each other. They are attracting each other, okay? Over here, these are definitely like, seem like they're pushing on each other. And that's because we might have like two north poles together, and the lines don't go from north to north, they go from north to south. Over here, they're going from north to south. So they're going to attract each other. They have opposite poles. All right, good, good, good. What happens to a compass when it's placed in a magnetic field? Again, very first day, you had a compass. Would we need to draw anything like this on the test? Ooh, great question. I would assume you would have to draw a magnetic field, okay? It won't have to be like this fuzzy version. It will probably be more like like something like this. Will you have to draw this? And so like you might have a magnet like this, and it's like draw the magnetic field around it. Okay, I'm not saying it's gonna happen, but it might happen. Okay, if it were to happen, this would be the kind of question it would be. It'd be more like, yeah, I think you probably got it. It's like, if this is a magnet, north, let's go like this. You might see something like this, maybe. I'm making this up as my head, and it'd be like, draw the magnetic field. And you would have to draw like that. You basically have to draw the basics, okay? So you don't have to get all like super crazy. Yeah, just do your best with that and you'll be fine, okay? The bottom line we'll be looking for is you're drawing from north to south. Great question. Okay, the compass when it's placed in a magnetic field. What's it going to do? Point to the positive charges. No. What? No. Magnets. Charges do come into play later, but it's the whole left-hand, right-hand rule stuff. So it's not going to point to any charges. It's going to line itself parallel to the magnetic field lines. Yes. So if you have, like, for example, a giant planet and it's got a magnetic field going from north to south and north to south, north to south, north to south. And if you put like a little tiny magnet in there, the magnetic field lines are going to line up parallel to those magnetic field lines from the planet. So that's what, parallel means. Parallel. Perpendicular would be like a T. So that's the answer. Okay, that's why compasses always point toward the north, because they just naturally turn to line up with the magnetic field lines that are coming from the north to the south. So, okay. Believe it or not, this is the first part of the unit. What is the direction of the current in the wire? So what we are seeing here is we got a wire, we got a current. Obviously, it's either going up or down. We don't know. But then we have this magnetic field here going, like kind of going to the left in front of the wire, curling around and going behind the wire to the right. Okay. And so for this, you would have to use, is there a force involved? There is no force involved. And so for this type of question, you will have to use the right-hand rule. So I'm going to try something really quick here. And this is going to be a little sloppy maybe, but I'm going to try it. I'm going to turn on another camera. Maybe. There it is. So I got another camera because I want to use my hand here. And I'm going to, and you should too, take your right hand, okay? And you need to basically curl your fingers in the direction that you're seeing. So this is not it. This is like the opposite. So I need to curl my fingers so that if, say, like this pen is that wire, if I grab it so that my fingers come around, I know it's dark. This is maybe if I do this. I grab it so my fingers go around the front to the right and then around the back. What direction is my thumb face? Hi, Jack. Then my thumb face is down. Okay, so you grab the wire with your right hand and go away camera. Okay, and it faces downward. So the answer is down. Where'd my pen go? So you could just literally draw an arrow down. Okay. So this is the right hand rule. There's no force involved. Okay. Right hand rule, no force. Hi, everybody. What is the direction what direction is the current in this wire? Okay, what is even going on here? All right, well, it points to the wire in the middle, and what it's saying is that that wire is basically heading out of the screen right toward you. Or maybe the current is going away from you right into the screen. That's what we don't know. So once again, you need to, is there a force involved? No, there's no force involved. And so what we need to do is I'm going to take my right hand. I'm going to curl my fingers so that they match the direction of the circles. And what that means is my thumb, what happens then is my thumb is pointing directly out of the screen. Okay, so that's the direction coming out of the screen. What do I mean by that? Well, or how do I represent that? Probably is the better question. So if you remember, coming out of the screen looks like this. So we could say out of the screen, which is a little confusing. I'll tell you, but that's how we represent it. That is the answer. So answer. The other one going into the screen looks like this. Okay, into screen. It looks like an arrow going away from you. Okay, but that is not the answer. Not answer. Okay, so that's how you represent it. Okay, what direction? We're still on the first part of the unit. What direction is the magnetic field at X? Okay, this is another one where you're going to have to, first of all, is a force mentioned? No force. So therefore, you use the right hand rule. All right, those little 3 dots mean therefore. It's a very nice, easy shorthand. So no force means we use the right hand rule again. So do that at the X. So what that means is this. I'm going to see about, let's do the little camera again. And I don't know if this is useful at all, but I thought, you know, me going like this to this screen doesn't really do anything for you. So this way I could at least sort of interact with it. So if I point my thumb in the direction of the current to the left, to your left, then my fingers are curling around. They're basically going up and over the top. They're going behind it, and then they're coming out at you where the X is at. Do you see that? So like you reach over, you grab you with your right hand. Your thumb is pointing in the right did I say the right? Into the left. It's pointing to the left, and you grab that wire, and your fingers are curling over the top and coming out of the screen at the bottom. Okay, so that is the right hand rule there. So what direction is it moving? The answer, again, is out of the screen. Okay, out of the screen. Okay, because, and I'm going to try to draw, it's not going to work, but I'm going to try to draw it. Because of the right hand rule, this goes behind it, okay, and down behind it, and then it comes out in front, and then it goes in front of it. So it doesn't look 3-dimensional. I cannot draw it. You just can't draw 3-dimensional without like taking special time, doing shadows and all that. So use your right hand. All right. So at the bottom, it's coming out of the screen. All right. What about this one? Well, I kind of literally just did it. It's the same exact like direction. They're both pointing to the left. So if I remember correctly, that means this is going into the screen right here. So it goes, remember, over and up at the top, and then yeah, it comes out the bottom. So in to the screen, or whatever you want to call it, away from you, right? Like however, like that's why we draw a symbol, okay? Because that symbol tells us the exact direction it's going into. All right. Current carrying wire runs through an area with a magnetic field going into the screen. What direction is the force on the wire? Oh, I just said the F word. Force. That means we have to use the left hand rule. All right. What is the left hand rule? Allow me to show you. FBI. Okay. Hi, I just hit the microphone. Remember, force is involved, you got to call the FBI. So what does that mean? On your left hand, you got to make the symbol. All right. And then you got to make everything 90 degrees to each other. So 90 degrees between your thumb and your pointer finger, 90 degrees in the other direction for between your pointer finger and your middle finger. And then your middle finger and your thumb should also be at 90 degrees to each other, so that, yeah, they look like this. So everything is at 90 degrees to each other. And your thumb is F, force. Your pointer finger is B, magnetic field. And your middle finger is the direction of the current. So bear with me while I try to do my little camera trick here. Where did it go? Boink. Nope, there we go. All right, this is going to be a little sloppy, so bear with me here. So a current carrying wire runs through the area with a magnetic field going into the screen. Okay, magnetic field is your FB, that's your pointer finger, so you're going to point that right at the screen, okay? And it says, or it shows the current, I's right there, it shows the current is moving to the right. So that's going to be this, your middle finger is pointing to the right. That means that your thumb is pointing upward on your left hand. That means that is the direction of the force. Okay, so one more time. B, the magnetic field, is going into the screen. So I'm pointing right at the screen. You're going to point right at the screen. The current is going to the right. So you're going to point directly to the right. You're going to point in the same direction as this arrow is showing you. Okay, with the eye, the current. And your thumb is pointing upward. So that means the force is to the, well, up. It's up. Okay, so I'm going to, like before, where'd my little thingy go? Hello, pen. There it is. I can never find it. Up. That's the answer. Up. Okay. Toward the top of the screen. Okay. I think this is the last of the hand rules. So one more thing. A charge is moving through a leftward magnetic field such that it experiences a downward force. Ooh, there's the F word again. Okay, so force is involved, so we're gonna have to call in the FBI. We're going to call in the left-hand rule. Okay, left-hand rule. What direction is the charge moving? Okay, this one's a little weird looking, but it's okay. Everything is the same as we've been doing. All right, you just take your left hand, and this is gonna hurt me though. It's moving through a leftward magnetic field. Oh, man. Okay, so I have to take F. No. Well, actually, that F, this looks like it might be the direction of the current, but it's not. This is the force. So that means force is, that F right here. That arrow is showing the direction of the force acting on the charge. It's not showing the direction of the charge. So just kind of be aware of that. So a charge is moving through a leftward magnetic field. Where were we? All right, FB. So my my right hand is going to have to point to the right. Woo. Or what did I say? My pointer finger is going to have to point to the left. And the force is downward. So I'm going to have to turn my whole left hand over. So my thumb is pointing down, my pointer finger is pointing to the left, and that leaves my middle finger, which is the direction of the current, pointing right at the camera. It's pointing right at me. And so my answer is, ow, right at me. Okay, coming out of the screen, if you will. And so yeah, look back at that. You have to rewind that one if you want to see that again, because I think I would need a cast if I tried to do that again and get a broken wrist or something. So bottom line is coming right at me, right? So I'm going to draw, so out of the screen for the current. All right, because let's do this. No, you know what? I think we're good. All right, if you got any more questions, let me know. All right. I'm going to pause here for a moment, let the thing catch up, but I'm just going to talk about electromagnets and all that, and then we're getting to be almost done. This next part doesn't involve any hand thingies, so if you got any questions about hand things, let me know. I'll go back, all right? The delay will make it so it'll be obvious that there's a delay, but I definitely would rather go back. This is a live stream after all. Okay. What would cause current in a circuit? Which would cause a current in a circuit? Well, let me just do something really quick. Here we go. Wait, when is the test again? Friday. So right now it's Tuesday. A closed circuit moving perpendicular to a magnetic field lines. It is not tomorrow, no. It is Friday. Yeah. All right. So first of all, a closed circuit means that it's closed. You have your it's a loop, right? You got your battery, you got whatever resistors you're going to have, and you have a closed loop. So it cannot be open, because if it's open, you will not get if it's open, let's say there's a switch right here, and here's my battery, and then here's my resistor. I drew that a little bit better. You will get no current and therefore no magnetic field. Okay, no magnetism. It will not be a magnet. So if you want a magnetic field, you automatically have to have a closed circuit. And the other thing, remember I said you had to have, is it has to be moving. So this stationary means it's staying still, so that can't be it. So your answer is going to be A. It has to be moved. I just showed it to you in class today when I moved the giant coil of wire through a magnetic field. Okay, that's what I did. I moved it. If you remember, if you were in class, you saw me move a giant coil of wire through a magnetic field with a light bulb attached to it, and the light bulb lit up. Okay, and if you hold it still, nothing's going to happen. There has to be the B, or the F, the force has to be there, has to be moving to force things to happen. So, all right. Motors, generators, and electromagnets have a lot in common. They have a coil of wires. Okay, you built a motor. You've built an electromagnet. Today, I told you that motors and generators are essentially very, very, very much the same thing in a lot of ways. One just uses electricity to cause motion, and the other one uses motion to make electricity. Okay, that's boiling it down very simply, but that's basically what it is. They're just reverse of each other in a lot of ways. So you need a coil of wire for all of those. What else? Make it stronger. Increase the number of loops in the coil. Yes, more loops in the coil will make it stronger. Increase the strength of the permanent magnets. Well, it's asking specifically about the motor, okay? And in a motor and a generator, you need a permanent magnet. And yeah, if you increase the strength of the magnet, you're going to get a stronger push. It's going to push those electrons more, with more strength. Increase the current running through the coil. Yes, that will also cause, so now the electrons, there's more electrons, and they're pushing against the magnetic field. More things to push means it's going to push more. And so all three of those are going to make the motor stronger. Okay. Cool. All right. You'll be expected to know how to do this, how an electric motor works, okay? You can maybe describe how to make some of the other things we've talked about. Maybe not the electromagnet. The electromagnet is sort of too simple. Think more complicated. Electric motor, a generator, a speaker, things that use the concepts that we've been exploring the last couple of days, okay? So how does it work? Well, this is a summary. All right, you have your coil of wire. This is my wonderful drawing. A battery and a permanent magnet. Okay, you need those three things. Make sure you list them. Right, a coil of wire, a battery, and a permanent magnet. The current in the coil. So you have the current coming out of the battery. It goes through the wire. It goes around and around and around and around and around, okay? And that current is creating a magnetic field. And the current goes, it finishes up by going through the battery and loops around again and again. So that current causes a magnetic field where I'm at. The current in the coil turns it into an electromagnet. So now your coil is an electromagnet, which is repelled by the permanent magnet. Okay, done. And so the North Pole here, hang on, the North Pole here will repel the North Pole here. The current has to either switch direction or alternate between off and on, so the permanent magnet will always repel the coil. So that's what you did. You sanded down only half of the wire over here so that when it flipped upside down, the current could no longer travel through the wire because of the insulation that you left down there. And so the current stopped. And so it was no longer a magnet. And so the coil kept spinning around because of its inertia. And then it repeated. All right. So this was in the reading that you had to do. You could also find explanations online. You could ask AI to explain this magnet to you. You might have to ask it to summarize it, remind it that you're, in high school. You need to keep it simple to, like you don't need to get into the specifics of it. But okay, and so look that up again. Ask me if you have any questions. And finally, make sure that you can explain these things. Explain how to build an electromagnet. Explain how you can build a motor and a speaker. Okay, make sure you know how those work. Coils of wire. Which one requires the battery? Which one doesn't? Which one is going to generate electricity? Which one? What about the iron core in the electromagnet to make it stronger? Okay, and that's basically it. So does anybody have any questions? I'll wait here a couple seconds, and then if not, then you can always ask me questions later. But I'm going to kind of stall here. So like I said, there's no math. So the strategy for studying for this test is a little bit different than all of our other ones. I mean, there was still elements of memorization that you had to do, but this is all memorization. So maybe you make the flashcards for this one. Maybe you use the Cornell notes and you fold it over and you quiz yourself. Maybe you go on Quizlet or some other like study app that's out there. Maybe you ask ChatGPT, hey, I need to like put in the standards. Go and what are we teaching? Can you quiz me on electromagnetism and maybe it will, that's about it. So, all right. Hopefully this is helpful. I enjoy doing it and very good. Let me know if you got any questions and good luck. You will do amazing. Bye.